Hello, my name is David Nedelkov, and this is my Lab 6 report of Physics 2212, titled Magnetic Molasses, Faraday's Law. This video presents my computational model of a magnet falling through a conductive tube and the physics explaining the behavior. The purpose of this lab is to model how a bar magnet interacts with a conductive tube as it falls and to use Faraday's law to explain why the magnet slows down. Instead of collecting new experimental data, we used the model to replicate the well-known magnetic braking effect. The main result is that induced currents inside the tube create a magnetic force that opposes the magnet's motion, causing a dramatic decrease in the falling speed compared to free fall. The physics behind this lab relies on Faraday's law, Lenz's law, and the magnetic dipole model. A changing magnetic flux induces an EMF given by minus d phi b over dt. Lenz's law tells us that the induced currents oppose the change in flux. The magnet is modeled as a point dipole, which lets us calculate the magnetic field at any point. Finally, we use the Biot-Savart law to compute that field generated by each induced ring current, and the force on the magnet is the gradient of the dot product of its dipole moment with that field. In the model, the system is the falling bar magnet. The surroundings consist of Earth, which provides gravity, and the conductive tube, which we represent as a stack of independent current loops. We assume the tube is fixed, the rings do not interact with each other, the magnet behaves like a point dipole, and air resistance is negligible. These simplifications allow us to use a computational solution that still captures the main physics. The physical setup described in the original Faraday's Law lab involves dropping a magnet through a vertical aluminum tube. As the magnet moves, it changes the magnetic flux through the tube, creating induced currents that oppose the motion. For lab 6, we simulate this setup rather than performing new measurements, but the underlying idea is the same. Eddy currents create magnetic damping. For the code, I added the dipole B function to compute the magnetic dipole field, then completed the dflux over dt function using the analytic formula from class. I used Faraday's law to turn that into the induced current, and the existing code handled the coloring and the force. After that, Newton's second law updates the magnet's motion. The simulation produces a real-time visualization of the magnet falling through the tube. The rings are colored red or blue depending on the direction of the induced current, and the brightness indicates the magnitude. The model also generates live plots of velocity versus time and position versus time, helping us see the dynamics clearly. The velocity time graph shows that the magnet does not accelerate uniformly. Instead, as the induced current grows, they create an upward magnetic force that reduces the acceleration. Eventually, the magnet approaches a terminal velocity where the magnetic force and gravity roughly balance. The position time plot also shows the motion slowing compared with free fall. The model clearly demonstrates the magnetic braking effect. The strongest induced currents occur when the magnet is near the center of the tube, where the flux changes fastest. Flipping the magnet reverses the direction of the induced currents, but the braking force remains the same because Lenz's law depends only on the opposition to flux change, not the magnet orientation or the actual flux. There are several limitations to the model. The rings are treated as independent, but in reality, they interact electromagnetically. Air resistance is ignored, and the magnet is approximated as a perfect dipole. The aluminum thickness may vary, and the computation model doesn't include full electromagnetic back reaction. These differences can cause deviations between real behavior and the simulation. If the resistivity of the tube were lowered towards zero, the induced currents would become extremely large. That would produce a very strong upward magnetic force, causing the magnet to fall extremely slowly, approaching magnetic levitation. If we cut slots or holes in the tube, The loops would no longer be closed, meaning no currents could circulate. With no induced currents, um, there would be almost no magnetic braking, and the magnet would fall nearly in free fall. In conclusion, the computational model reproduces the key features of a magnet falling through a conductive tube. Faraday's law and Lenz's law correctly predict the induced currents and the resulting magnetic damping force. Although simplified, the model captures the essential physics of the magnetic Molasses effect and shows how changing magnetic flux can produce measurable forces. Thank you for watching.